So in this lecture we will get deeper into factorial designs. So factorial designs are those in which there are multiple factors, each one with multiple levels, and we studied not necessarily all combinations as we will see in these fractional factorial designs or in the screening designs. And, yeah, a particular kind of interesting factorial designs are those in which each one of the factors, let's say that we have k factors, and each one of the factors has two levels, so this will be a special case. And at the end we will study how to use blocking with factorial designs and how we can make factorial designs for quantitative factors, so not something having discrete levels but a whole continuous, and that is called response surface method. Okay, so let's start with the factorial designs. So let's say that we want to find the optimal combination of the number of meals and daily calories for a weight loss diet. So we are thinking of 3 or 5 meals, so that is a factor with two levels, and for the number of calories we are thinking of 3 different levels. So for each combination we may call it a treatment 1, treatment 2. So we have already seen this idea that all these factorial designs, they can be analyzed in a one-way ANOVA. But the problem with that analysis is that we see differences, but we cannot attribute those differences to the meals, to the calories, or to the interaction between the two. While the two-way ANOVA, it allows the factorial design itself, it allows to identify which is the contribution of the number of meals, which is the contribution of the number of calories, and which is the interaction between the two. So just to introduce some names, factor is the set of treatments of a single type, so the number of meals or calories. The level of a factor is a particular treatment within that set, so for instance the different numbers. And experimental treatment is a combination of one level from each factor, so 3 meals with 1500 calories is an experimental treatment. And then we make calculate the main effects that are the contribution of 3 or 5 meals, and we can compute interactions, that is comparisons between levels of several factors, so 3 meals and 1500 calories versus 3 meals and 1700 calories. So factorial designs test the main effects of each factor within a variety of other levels. So this makes so when you have tested 3 or 5 meals, you have analyzed them with many other possibilities for calories, so that makes your experiment more generalizable. It also allows estimating interaction between factors that the one-way ANOVA doesn't allow, and it reduces the number of samples with respect to the change only one variable at a time. So we saw this with the experiment of frogs and toads, dry or wet, and giving an hormone or not. So also they don't need to be complete. So let's say that in some experiments it doesn't make sense some of the combinations. So let's say that you have 3 factors, A, B, and C, and the combinations no, 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 or yes, 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 cannot be experimentally done. So doesn't matter, you don't do them, and we now know how this will translate into the system matrix of the least squares approach to solve for the components and the contributions of each one of these factors. And also you may design very complicated factorial designs. So let's say that you are comparing two chemicals, E and O, versus a control. Chemical O is an oil that requires a surfactant, and we have two possibilities for the surfactants, S1 and S2. The application can be performed with two different sprayers where you are changing the diameter of the droplets, and you will test the chemicals at 3 different concentrations. And we plan to do comparisons between the two chemicals, and the control, the main effects of the surfactants, the main effect of the sprayers, the main effect of the concentrations. And we may design our experiment in this way. So for instance, we will have the 3 chemicals, and chemical O has a surfactant, so we will make the combination of chemical O with surfactant 1 or surfactant 2. And also we have different sprayers, so we have this one with a sprayer 1, this one with a sprayer 2, this one with a sprayer 1 again, this one with a sprayer 2, the same for E and the same for the control. And we have multiple concentrations, so we will do one experiment with this combination, one with this second concentration, and one with this third concentration. And if we count how many O's we are having 12 O's, so we will have also 12 E's, and you can have 5, or we could expand it to 6 controls. So all the chemicals and controls, they have approximately the same number of samples. They don't need to be exactly the same number of samples, and we already know through all the methodology that we have developed along the course that this will translate into the properties of this system matrix. And then these properties, depending on what are the comparisons that we are interested in, they will have an impact on what is the variance of those comparisons. Let us go to factorial designs in which we have k factors and we have only 2 levels for those factors. So this was the experiment of the frogs. So you may remember that we had 2 species, 2 moisture conditions, previous conditions, and 2 possible levels of the hormone. And here are we had 2 replicates for each one of the combination, and here we have the values obtained for those replicates. Okay, so let us now we will become a little bit more formal. We will use a little bit of mathematics to try to generalize this kind of analysis to very general conditions. Okay, so let us call 1 the mean of the observations with no treatment applied. So we have 2 levels. We have 2 levels, P, Q, and R. We will call 0 to toads, frogs will be equal 1, wet will be 0, dry will be 1, control will be 0, hormone will be 1. So 0 or minus 1, it doesn't matter, it is just the naming. Okay, so let us call the mean 1 the mean of observations with no treatment, that is P equals Q equals R equals 0. So that means toads wet with control. So that will be 1. So let us call capital P the effect size when applying P equal 1. So P equal 1 is frogs. So it is the effect size, the extra that you get for being a frog. And a small p is the mean of all the observations that has P equal 1. So it is the mean of all frogs. So we take all frogs and we compute the mean of these numbers. And we proceed in the same way for all the others. So capital PQ is the effect size of P equal 1 and Q equal 1. A small pq is the mean of these observations, and so on. So for an orthogonal design, we learned that we could estimate the effect size of P as the difference between the mean of all the frogs minus the overall mean, or the mean of these people that of these animals that have P equal q equal 1, r equal -1. So it was the frogs, no sorry, toads, wet, and control. So we can estimate like that, but we can also estimate like this, and there are not a single, there is not only one way of estimating this effect size of frogs, but there are many possible combinations of the mean of frogs plus the mean of wet frogs divided by 2 minus the mean of toads, wet, and control, plus q. Q is the mean of dry divided by 2. So there are many multiple ways, and there is one particular way that is particularly important, that is this one. This one can be factored out in this way. So this -1 or +1 is this mean here. So, and this is very important because it is coming from a very general formula, and this general formula is given in this table. So let's say that these are the different means of the different factors that we have been talking. So this we already introduced, and now we put the elements of our model. So the elements in our model is they all have an overall mean, and then this doesn't have p, so we put p to minus. Q doesn't have q, we put it to minus, and r, it doesn't have r, so we put it to minus. Actually, if you look at the pattern is minus plus minus plus minus plus minus plus. This is minus minus plus plus minus minus plus plus, and minus 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 plus 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 plus. So once we have and we see that it is correct, right? So for instance, this one, it is plus p plus q minus r because it doesn't have r. Okay, so now we can multiply these two columns and obtain the column pq. So this is minus minus plus, plus minus minus, minus plus minus, and so on. And we can do the same for all the others. So this is pr, this is qr, and pqr is simply pq times r. So it is plus minus minus, minus minus plus, and so on. And now let's say that we want to estimate the PQR, for instance. So here we have the general formula that we need. It will be 1 over 4, and we will come to this factor later. So it is 1 over 4, and now minus this mean, plus this mean, plus this mean. So you see that these signs are giving us a way, a recipe to estimate PQR, the effect of PQR, as a function of the means of the different subgroups. And here you have the different formulas. So for instance, P, we want to estimate P, this will be 1 over 4, it is 1 over 4 all the time, P minus 1 times Q plus 1, Q plus 1, R plus 1, because we don't have Q and R. And let's estimate Q, so it will be Q minus 1, and this is P plus 1, R plus 1. So so it is all the time the same. So PQR, it will be P minus 1, Q minus 1, R minus 1. So this is a very, very general formula and can be generalized to any number of factors. And the mean is 1 over 8, and this one. And for each one of the k factors here, and the R replicates for each treatment. So what is the effect size? We have seen. So this is 1 over 2 k to the minus 1. That is where we have 3 factors. Then it is 1 divided by 2 to the square. So that is why we get 1/4 there, and we get 1/8 there. It is 2 to the k. But more importantly, we can compute what is the contribution to the variance of this effect size and the sum of squares of that effect. So this is the variance, and we see that it is divided by the number of factors and the number of replicates within each one of the treatments, and the sum of squares is given by this effect size. Okay, good. We can express that, so these formulas in matrix forms. We have taken all the 2k minus 1 that are dividing here, we have taken them to the other side for convenience, and then these are the estimation formulas for each one of the factors, and we see these are the means, and we see that we have very nice patterns of plus ones and minus ones. The colors is simply the plus or minus one. So we have in a matrix form, we have these are the effect sizes of each one of the main effects, interactions, and so on. These are the means, and what we see is that these ones are a matrix and times these means, and this matrix turns out to be orthogonal. So orthogonal is a matrix such that the inverse is this one. So I can solve for x, I can solve for this by simply computing the inverse. So the inverse will be this one, and this will give me the data generation model. So the data generation model that we have used so far, it was relatively simple. It was an overall mean plus something that depends on the treatment plus something that depends on the main effect of P plus the main effect of Q plus the main effect of R plus the interactions. But we can also do them in this way, and this way it is coming from this 1 over the determinant of U transpose. So for factorial designs, we can express this this image or this data formation model in a very precise way, in this way. So this capital P, capital Q, capital R are the main effects when the P is 1. And here I can take either the value 1 or 0, and J and K. So let's say that we are interested in what happens to toads dry control. So it is 0, 1, 0, so you substitute here 0, 1, 0, and then so I, J and K are 0, 1, 0, and then after the substitution you get this one. And now you try toads dry, so these two are the same, but now with a mode. So now K will be 1, and now it is this one. At some point you will be interested in comparing the hormone control for toads dry, for dry toads. So it will be this comparison, and this comparison you simply subtract this one minus this one. It is this. So it is the effect of the hormone, this is R. The effect of the hormone on frogs, this is PR. The effect of the hormone on wet animals, this is QR, minus the effect of the hormone on wet frogs, this is PQR. And each one of these estimates, we learned how to calculate those estimates. Each one of those estimates will have a variance. So we can substitute what is the variance of each one of these 4 elements, and it is this one. It is this one, that is sigma squared divided by 4, because we have 2 animals and we have 3 factors, so it is sigma squared divided by 4. So if we have the full model, so when we analyze, we use all the terms on the equation, then this comparison, we have 4 terms of this kind. So these 4 terms will have 4 times this variance. Let's say that we don't estimate the PQR at the third order interactions, then this term doesn't exist. And if it doesn't exist, then we are left only with 3 terms. So the variance of these comparisons is 3. And let's say that we have we don't estimate the second order interactions. We are left only with the model of main effects. Then this is the variance. So we see that depending on how many parameters we estimate in our model, we have more or less variance when we are comparing, or we are making this comparison. And that comparison is important because depending on the values, and here you have the values of this experiment, so here you have the values of this experiment. So depending on what is your analysis formula, you will have that there is no difference between dry toads in hormone or control if you use the full model. So if you use the full model, you see the standard error of that estimate is pretty large, and then this difference, although it is positive, it is also its 95 confidence interval includes 0, so you cannot reject the null hypothesis that there is no difference. And the same if you don't have the third order model, but if you don't estimate the second and third order models, now it is significant. So depending on what is your analysis formula, you may have a comparison that is significant or not. And so in general, factorial designs allow estimating many interactions, but it doesn't mean that you have to do it. So if you think that these interactions do not exist, you don't have to estimate them. And then you are leaving all these degrees of freedom for estimating the interactions. You are leaving them for the residuals. And then you will have more powerful tests. So in general, the simpler the model, the better. And the choice to remove these interactions must be done before doing the experiment, never after seeing the experiment results, because otherwise you are data snooping, and then you are taking decisions after seeing the data, which is not good. And these ideas can be extrapolated to more complicated factorial designs with 3 levels, 4 levels, and yeah, so we have kind of similar formulas for estimating the different effects of each one of these factors. If you have to replicate a factorial design, don't forget to randomize. So let's say that you have all these treatments 0, 0, 0, 0, 0, 1, 0, 1, 0, so on. You plan to replicate it, but then within each one of these replications you have to randomize. Okay, now we have learned an interesting idea. We can sacrifice estimating the higher order effects and give these degrees of freedom for the residuals, and this idea can be exploited to make experiments with just a single replicate. So for instance, let's say that we are interested in the survival of these bacteria under 3 different experimental factors. So we have 3 levels of sorbic acid, we have 6 levels of water activity and 3 levels of pH, and then the data will be the logarithm of the density measured after 7 days after the treatment. So we have 3 times 6 times 3 combinations, that is 54 treatments, and we will use a single replicate for each one of them. So this is the ANOVA table for this experiment. So we see that we have 5 degrees of freedom for the water activity. We have 2 degrees of freedom for the sorbic acid, 2 degrees for the pH, and we have the interaction. So we have A times S, so we have 5 times 2, that is 10. We have A times P, that is 5 times 2 again, and then SP, that is 2 times 2, 4. So in total we had 54 degrees of freedom, so 54 minus 1, and then if you count how many you have used for the main effects and the second order interactions, we have 33 in total, and then the last 20 they go for the third order interactions, but we don't want to estimate the third order interactions, so we leave them as residuals. So we have 20 degrees of freedom for the residuals, which are not a few, and then we can, with these 20 degrees, so we are confounding the third order interactions with the residuals, and then we can use these residuals to compare what is the significance of the main effects and the second order interaction. So we see that some of them are very highly significant. This one is slightly significant, but the others are not significant. So the problem with single replicate factorial designs is that it is difficult to use blocking, because in each block you should use a few treatments, and due to the lack of replication, there is no possibility to construct an unbiased estimate of the noise, so the noise is always confounded with high order interactions. So this will be all, and in the next section we will learn that even we don't need to try all combinations.